Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Mohammed bin Zayed University of Artificial Intelligence, K2-V2, a 360 open, reasoning-enhanced LLM. K2-V2 is a 70 billion parameter language model built from the ground up to be both powerful and fully open. The team's goal wasn't just to release another chat model, but to create a strong, reasoning-focused base that others can reliably build on. Unlike many open-weight models, K2 comes with full transparency. Model weights, training code, data composition, and even training logs are all available. In head-to-head comparisons, K2 holds its own against larger open-weight models like Qwen 2.572b and approaches the performance of Qwen 3.235b, especially on challenging reasoning tasks. The motivation behind K2 is simple. The strongest models today are mostly closed, and many open models are either underpowered or underdocumented. That makes it hard to study how reasoning emerges, and hard for practitioners to safely extend models to their own domains. K2 is meant to fill that gap. It's strong enough to matter on hard benchmarks, but also transparent enough that you can see exactly how it was trained and continue training it yourself. The authors explicitly design it as a foundation for reasoning, long context use, and tool integration, not just as a generic chatbot. K2 development follows a three-phase pipeline. First, a classic but carefully tuned pre-training phase on about 12 trillion tokens from the TXT360 corpus, builds broad knowledge and language skills. Second, a mid-training phase, called TXT360 Midas, pushes the model into new territory. Very long context windows up to 512,000 tokens, and heavy exposure to synthetic reasoning traces. Finally, a light supervised fine-tuning stage adds instruction following, tool use, and 3 distinct levels of reasoning effort. The result is a model that already performs strongly, but is clearly prepared for a later reinforcement learning phase to push reasoning even further. Under the hood, K2 is a fairly standard but large decoder-only transformer. It has 80 layers, a hidden size of just over 8,000, and a feed-forward network that expands to nearly 29,000 dimensions. Attention uses 64 heads, but with grouped query attention so that only 8 p-value heads are stored, saving memory and compute. For positions, the model uses rotary embeddings with a base frequency tuned for 8K context during pre-training and later adjusted during mid-training to support much longer contexts. The backbone of K2's knowledge is TXT360, a large, carefully curated corpus. Most of it comes from English web pages, heavily filtered and deduplicated across 99 common crawl snapshots. On top of that, the team adds synthetic question-answer pairs grounded in real documents, a large body of scientific papers, math corpora, code, Arabic web text, and structured sources like legal opinions and patents. A key design choice is global near deduplication. Every document is made unique first, and only then selectively upsampled based on quality signals like natural duplication across years. That lets the authors control the training distribution, instead of inheriting the web's raw repetition. To make the most of their data, the team trains a custom byte-level BPE tokenizer. It's tuned so that English and modern standard Arabic are tokenized efficiently, with fewer tokens per word than many generic multilingual tokenizers. On the web side, they start from raw common crawl and run a multi-stage pipeline. Language ID, URL filtering, quality filters, PII removal, and both exact and near deduplication. From this, they carve out TXT360cc, a broad web corpus, and TXT360 Best of Web, a higher quality slice selected using the ProX document filter and a format score that rewards clean structure like headings and code blocks. Even in pre-training, K2 uses synthetic data, but in a conservative way. Rather than free-form hallucinated text, the team generates question-answer pairs grounded in real web pages from the Best of Web subset. A Mistral 7B model reads each page and produces several QA pairs, which are then appended to the original text. During training, the model sees the passage and immediately the questions and answers that refer back to it. To ensure quality, another LLM acts as a judge, checking whether each question and answer is fully supported by the passage. On a sample of 8,000 documents, over 95% of pairs pass this test. To support serious mathematical and coding ability, K2 leans heavily on specialized corpora. MegaMath Web and MegaMath Code provide a large math-aware slice of the web and math-related code, with equations and symbols preserved. These are complemented by other open math datasets like DM Math, InfyMM Web Math, Open Web Math, and the textbook portion of MathPile. On the code side, refined code supplies cleaned GitHub code, which is then transformed into fill-in-the-middle format and repository-level, topologically sorted sequences. All of these math and code sources are deduplicated against each other to avoid redundant learning and benchmark contamination. Training a 70B model at this scale is as much about stability as it is about data. K2 is trained on about 12 trillion tokens, with a global batch of nearly 10 million tokens per step. The learning rate follows a cosine schedule, but the team found that decaying all the way to zero caused the parameter norms to freeze, suggesting stalled learning. They instead stop at about 1% of the peak learning rate. To guard against divergence, they monitor the loss with a robust sliding window detector that flags wide, persistent spikes. When such a spike appears, the system automatically rolls back to the last good checkpoint and restarts. Most of these events happen early in training and become rare later on. On the system side, K2 runs on a cluster of NVIDIA H200 GPUs, each with 141 gigabytes of memory and high-speed InfiniBand networking. The team uses a hybrid parallelism strategy, tensor parallelism and sequence parallelism within nodes, and data parallelism across nodes. They deliberately avoid pipeline parallelism because the per GPU batch size is small, which would create large pipeline bubbles and waste compute. To fit the model and keep throughput high, they rely on activation recomputation, bfloat 16 precision, and flash attention too. An in-house job manager monitors hardware faults and restarts jobs automatically when needed. After pre-training, the authors don't jump straight to instruction tuning. Instead, they run a mid-training phase with very specific goals. First, they want the model to handle extremely long contexts, up to 500,000 tokens, without losing coherence. Second, they want to expose the model to explicit reasoning traces and diverse reasoning styles so that thinking becomes a native behavior. At the same time, they're careful not to destroy performance on classic benchmarks like MMLU. That means mixing synthetic reasoning data with a healthy dose of natural web and book text, and keeping at least 30% short context data in every stage. Mid-training is broken into 4 stages. Stage 1 keeps the original 8K context but shifts toward higher quality data and starts injecting reasoning traces. Stage 2 jumps to 64K tokens and doubles the rote base frequency to 1 million. Stage 3 pushes to 128K tokens and increases the rote base to 10 million, which turns out to be critical for long context performance. Stage 4 reaches 512K tokens, still with a 10 million rote base. To make this feasible, the team gradually increases context parallelism, so that attention over these huge sequences is split across GPUs. Throughout, they keep the learning rate low and constant to avoid destabilizing the model. The mid-training dataset, TXT360 Midas, is built to fill gaps that natural text doesn't cover well. For math, the team collects over 250 million unique problems from permissively licensed sources and solves them using reasoning-enabled models like Qwen332B and GPT-OSS120B, capturing full thinking traces. Beyond math, they define more than 100 reasoning behaviors. Things like dual-process reasoning, detective-style inference, or red team versus blue team analysis, and apply them to real user queries to generate rich synthetic examples. They also generate non-reasoning behaviors, such as planning or technical manuals, and mix in institutional books and curated web data to provide long, coherent documents for context training. To avoid overfitting to long documents and forgetting how to handle short prompts, the authors carefully bucket data by length. In Stage 1, everything is short. In Stage 2, most tokens come from documents between 8K and 64K tokens, but 30% are still short. Stage 3 shifts almost half the tokens into the 64K to 128K range. By Stage 4, the majority of tokens come from very long documents up to 512K, yet about 40% of the training signal still comes from short contexts. This deliberate mix helps preserve performance on standard tasks, while the model learns to reason over very long inputs. For mid-training, the team moves off Megatron LM and onto their own PyTorch-based framework. This gives them more control over context parallelism and fully sharded data parallelism. They tokenize on the fly, which makes it much easier to adjust data mixes without regenerating huge token files. They also implement an online best-fit packing algorithm that packs multiple documents into each sequence with almost no truncation and only a handful of padding tokens per 65K token sequence. For context parallelism, they use a straightforward all-gather of keys and values across context parallel ranks, overlapping communication with query computation. In practice, This simple design outperforms more complex schemes like ring attention for their setup. On broad knowledge and reasoning benchmarks, K2 performs well, though not always at the very top. On classic MMLU, it lands around 75%, behind Qwen 2.5 72B, but competitive with other large open models. Where it really shines is on more challenging variants like MMLU Pro, where the mid-3 checkpoint reaches nearly 60%, the best among comparable open models. On Big Bench Hard, K2 also posts strong scores in the low 80s, and on Truthful QA, it outperforms many 70B scale baselines. These results suggest that the mid-training curriculum improves deeper reasoning and robustness, even if raw factual recall isn't maximized. The biggest gains from mid-training show up in math and logic. On the math benchmark, K2's mid-3 checkpoint reaches almost 95% accuracy when evaluated with a reasoning-style prompt. GSM-8K, a standard grade school math dataset, climbs into the low 90s. On AME 2025, a very challenging competition set, the base model starts at 0 and rises to over 50% accuracy at mid-3, which is remarkable for a base model without RL. On synthetic logic puzzles like Knights and Knaves with 8 people and ordering tasks with 30 items, K2's mid-4 checkpoint matches or exceeds the performance of specialized reasoning models like DeepSeek R1 and O3 Mini High. On long context benchmarks, K2's mid-4 checkpoint shows stable behavior up to 128,000 tokens. On Ruler, scores drop gradually as context grows, but without the sudden collapse seen in some models. On the needle in a haystack benchmark, K2 maintains over 95% accuracy even at 128K tokens. The authors find that increasing the ROPE base frequency to 10 million is essential. A lower base of 1 million leads to degraded performance at long lengths. Interestingly, a smaller model that's explicitly trained for long context can outperform a larger one that isn't, underscoring that specialized long context training matters more than just parameter count. Instead of training separate instruct and thinking models, the team fine-tunes a single K2 model to support 3 reasoning efforts. These are triggered by special tokens in the chat template, a standard think block for high effort, and faster variants for medium and low effort. Only the last assistant turn contains visible thinking. Earlier turns have their reasoning stripped to save context. This design lets users trade off latency and accuracy at inference time without switching models. The supervised fine-tuning uses about 10 billion loss tokens across roughly 10 million examples, spanning math, code, STEM, chat, safety, and tool use. The SFT dataset, TXT363 efforts, is built around high-quality question-answer pairs. Questions come from permissively licensed datasets or synthetic generation, and answers are regenerated using GPT-OSS 120B at low, medium, and high reasoning efforts. The mix covers math, code, STEM, general chat, instruction following with verifiable constraints, self-identity, and safety. For agentic behavior and tool use, the team simulates multi-turn teacher-student dialogues, sometimes with tools in the loop, so the model learns to plan, call tools, and critique solutions. Overall, about 40% of lost tokens use high reasoning effort, 35% medium, and 25% low, giving the model a rich spectrum of thinking styles. Supervised fine-tuning runs on the final mid-training checkpoint with the same long context configuration, 65,000 tokens per sequence and a 10 million rope base. The team again uses online best fit packing, which is so effective that they see essentially no truncation and only a couple of padding tokens per sequence on average. That means almost every token contributes to the loss. They train for 3 epochs over the SFT data, about 6,000 steps in total, with a cosine learning rate schedule that peaks at 2 times 10 to the minus 5 and decays to 10% of that. The result is a relatively light SFT pass that still significantly improves usability. After SFT, K2 becomes a capable general assistant with strong reasoning. On Long Bench V2, the high-effort mode reaches over 42%, beating many reasoning-oriented models except the very largest. On Arena Hard V2, which uses a judge model to compare chat quality, K2 High scores around 62, on par with much larger systems. On IF Eval, which tests strict instruction following, K2 High hits 90%, and on the Berkeley function calling benchmark, K2 Medium achieves an overall score above 52, outperforming Qwen 2.5 to 72B and Llama 3.3-70B, especially on multi-turn tool use where maintaining state is hard. The 3 reasoning efforts don't help all tasks equally. On challenging math and science benchmarks like AME 2025, HMMT 2025, and GPQA Diamond, performance climbs steadily as you move from low to medium to high effort, with longer and more detailed reasoning traces. On easier tasks, the gains are modest, and sometimes extra thinking just adds latency. Interestingly, for function calling, medium effort tends to be the sweet spot. High effort can overcomplicate things and hurt accuracy. The high effort mode also shows a wide spread in generation length, suggesting that the model is starting to adapt its thinking depth to the difficulty of each problem. To gauge how much headroom K2 has for further reasoning improvements, the authors look at K metrics. As they sample more solutions per problem, success rates on math, coding, and instruction following benchmarks rise sharply, especially in high-effort mode. That means the model already knows many correct answers. It just needs better guidance to pick them consistently. They also sweep the sampling temperature and find that performance improves up to around 1.0, then starts to drop, with a sharp fall beyond 1.2. This defines a useful exploration zone for future reinforcement learning. High enough temperature to explore diverse reasoning paths, but not so high that quality collapses. One of the most interesting parts of the paper is a longitudinal study of K2's behavior over time. The team saves 10 checkpoints across pre-training and mid-training, then has a strong LLM evaluate their responses across 18 capability categories, from logical reasoning to planning and tool use. Early checkpoints show classic failure modes: repetition, shallow answers, and confusion. As mid-training progresses, the model starts to produce coherent plans, multi-step reasoning, and robust handling of ambiguity. The authors describe 3 phases: the emergence of chain-of-thought reasoning, the scaling of that reasoning to long contexts, and finally a specialization phase, where intense math training can slightly erode some generalist behaviors. The qualitative examples make these shifts very concrete. Before mid-training, the model often falls into loops or repeats parts of the prompt when faced with tricky algebra or ambiguous instructions. By stage 1 of mid-training, it can solve a constrained algebra puzzle, step by step, and present a clean final answer. By stage 4, it can lay out a detailed plan for organizing a scientific conference or designing a calendar and email management system, complete with tools and timelines. At the same time, the authors show cases where the highly specialized model overthinks and never produces a final answer, highlighting a trade-off between raw reasoning power and pragmatic communication. Safety is a major focus of the K2 release. Using the Libra eval framework, the team tests the model on 72 different safety and adversarial datasets, sampling about 200 prompts from each. Across all of these, K2 produces safe or desired responses about 86% of the time, and it consistently outperforms their earlier K2 Think model. It does especially well in domains that require careful knowledge and regulation, like chemistry, biology, financial compliance, intellectual property, and medical advice, as well as in socially sensitive areas like hate speech and extremism. The safety analysis also surfaces clear weaknesses. On benchmarks like OR bench and the false positive split of do not answer, K2 sometimes refuses harmless prompts that merely look risky on the surface. It remains vulnerable to some jailbreak attacks, which is unsurprising given how fast jailbreak techniques evolve. Because K2 is meant to be fully open, the team did not try to hide system prompts or internal instructions, so it's not suitable as is for deployments that require prompt secrecy. Finally, they observe thinking response divergence. In some cases, the reasoning trace contains sensitive information, like a hidden password, even though the final answer refuses to reveal it. Addressing this gap between internal reasoning and external behavior is an important open problem. Stepping back, K2-V2 delivers a rare combination: a powerful 7DB model that is also fully open and deeply documented. The mid-training strategy, injecting reasoning traces and long context data before any RL, proves extremely effective, especially for math and logic. The 3-effort supervised fine-tuning shows that a single model can flexibly trade off speed and depth of reasoning at inference time. At the same time, Passett K-curves and safety analyses make it clear that there is still plenty of room to grow. Reinforcement learning for reasoning, better calibration of refusals, and tighter alignment between thinking traces and final answers are all natural next steps. For the community, K2 offers not just a model, but a complete, reproducible blueprint for building and evolving advanced reasoning systems.